Take a protractor to a fresh honeycomb, and you will find every wall of every cell meets its neighbors at exactly 120 degrees. It happens on every wall, in every hive, anywhere on Earth. The colony builds these storage tubes out of wax, and wax is brutally expensive. A bee must consume several grams of honey to sweat out a single gram of building material. That creates a ruthless evolutionary pressure. The bees must divide a flat space into equal areas, while using the absolute minimum total length of wall. Watch how a flat sheet can be tiled with no gaps. You have exactly 3 regular options. Squares fit perfectly, but the corners are wasteful. Equilateral triangles are even worse. The hexagon wins out because it comes closest to being an efficient circle, while still agreeing to share a wall flatly against its neighbors. The design is so ruthlessly efficient that Charles Darwin himself studied his friends' hives. He viewed the honeycomb as the single most exquisite instinct natural selection had to offer, an architectural triumph achieved blindly by thousands of individual builders. To a mathematician, biological instinct is not a proof. Proving the bees right meant being certain that straight-walled hexagons beat every possible competitor at once. That includes an infinite wilderness of wobbly, curved walls that might bulge outward to steal a little cheap area from a neighbor. Humanity suspected the bees had the optimal shape, but knowing it for certain took 2,000 years. The gap between recognizing the pattern and proving it mathematically was immense. It was not until 1999 that an American mathematician named Thomas Hales finally closed the wilderness. He proved that no tiling, straight-walled or curved, could ever beat the hexagon. But to do it, he had to reduce all the local possibilities to thousands of explicit cases and check them using brute computation. We finally reached absolute certainty. The bees had been right the whole time. Yet the mathematical proof required hundreds of pages of text and gigabytes of computer code, a messy, exhaustive human effort to verify the effortless elegance of an insect. The moment you leave the flat sheet and start stacking things in space, the same geometry problem becomes vicious. If you want to pack identical spheres as tightly as possible, you arrange a bottom layer and place the next spheres into the dimples of the first, forming the classic grocery store pyramid. In 1611, the astronomer Johannes Kepler claimed that this obvious stacking, which fills about 74% of space, is the absolute best arrangement that can ever exist. He argued that no chaotic, jumbled arrangement could ever squeeze past it. Take one central sphere and see how many identical spheres can touch it at the same time. You can easily fit 12 around the center, but when they are in place, they do not quite fill the space. There is a tiny bit of slack, almost but not quite enough room to sneak in a 13th sphere, a detail that sparked a famous disagreement with Isaac Newton. That slack is a nightmare. It allows the neighboring spheres to slide around in infinite random configurations. Ruling out every possible chaotic rearrangement to prove that a 13th sphere can never fit, or that Kepler's 74% density can never be beaten, requires hunting demons of probability that break traditional geometry. This reveals a harsh limit. Our physical intuition is trained entirely in a 3-dimensional nursery. As we add dimensions, the amount of slack space grows, and the infinitely messy spatial possibilities quickly outpace our ability to picture them. Moving into higher dimensions sounds mystical, but an 8-dimensional point is simply a list of 8 numerical coordinates. It is a mathematical address, nothing more. The problem is that in these higher dimensions, the corners of mathematical space pull away rapidly. The volume opens up, creating exponential slack and allowing for vastly more neighbors. The wilderness of possible packings becomes practically impossible to lock down. Then, in 2016, a Ukrainian mathematician named Marina Vyazovska found a shortcut through the wilderness. She bypassed the need for brute force supercomputers entirely by designing a single, impossibly perfect mathematical measuring function. In a sleek 23-page proof, she demonstrated that in exactly the 8th dimension, an arrangement called the E8 lattice behaves like a crystal of pure arithmetic. Every sphere touches exactly 240 neighbors with 0 chaotic slack. The formula was so sharply tuned that within a week, she and her collaborators adapted it to conquer the 24th dimension as well. There, a structure called the Leech lattice locks spheres against nearly 200,000 neighbors. A century-old problem fell twice in 7 days. We still do not know the best way to pack spheres in the 5th dimension, or the 6th, or the 100th. Mathematical elegance on this scale exists almost exclusively in these few invisible high-dimensional rooms of the universe. If packing spheres in 24 dimensions sounds like pure abstraction, look at your phone. Every text message or video stream you send is converted into a list of numbers. By definition, that makes every message a precise mathematical point in a high-dimensional space. The physical world is noisy. Interference jitters those numbers, smearing your precise point into a fuzzy sphere of static. To prevent data corruption, engineers space allowed points so their spheres never touch. A corrupted point simply snaps back to its true center, erasing the error. Sending information quickly means cramming as many of these allowed points into the space as possible without their static spheres overlapping. The entire foundation of modern communication is a literal sphere packing problem. In 1949, engineers discovered the Golay code, an error-correcting blueprint so robust that it carried pristine color photographs from the Voyager probe across 1 billion miles of screaming cosmic void. The Golay code and the 24-dimensional Leech lattice are the exact same mathematics, just wearing different costumes. That identical 24-dimensional geometry operates constantly inside the phone in your pocket, silently keeping every text message clear by snapping corrupted data back to its perfect center. The bee packs wax to survive, and humanity packs meaning to communicate. They are identical optimizations of space. Evolution ran a brutal, blind search over millions of years to find the cheapest design, while human intellect took centuries of exhaustive logic to prove why that answer was inevitable.